Hello.
Yeah,
Yes,
I'll start.
cool.
Yeah, can you guys see my screen?
Yeah, I mean, it's still loading for me. Yeah, now I can see it.
Okay, cool. So, this talk is kind of based on a book I read last year during the summer. It's called Intuitive Topology by V.E+F. I'll present my references at the end anyway. So, yeah, so what is topology? And Prasolov gives a very cute, intuitive definition of topology in the preface that I have like lifted verbatim. Like intuitively speaking, topology studies those properties of geometrical objects that remain unchanged under transformations called homeomorphisms and deformations. So I wrote the definition of homeomorphism here for Varun, but like Varun isn't here, so fine, we'll just skip that because we all know it. A deformation is like it's kind of like stretching or like squeezing an object and changing its shape uh, while making sure that the object doesn't tear or like you don't glue two parts of the object together. Like, there is a more involved mathematical definition of deformation, which we'll do in algebraic topology next semester. It's kind of like you have this map which goes from like which covers an entire topological space, and that like map will kind of take some parts of the topological space and like bring them towards another part of the space, and the other parts of the space which are in the part of the space that we want to squeeze the object into will just work as an identity map. But yeah, let's not get into all that. English definition of deformation is just sufficient for what we will do today. So yeah, so here is my favorite topology meme. A coffee mug and a donut are the same thing. And this is how the whole like deformation process of changing a donut into a coffee mug works. So any questions? No, right? Okay. I'll just move on to the next one. Thank you, Anand. Next, let's look at what a knot is. So a knot is kind of like an elastic string, but the ends of the string are tied together or glued together so that like it's just one smooth thing. A deformation of a knot is not considered to be different from the original knot. Like this statement is a very important statement, which yeah, we will see in the next note why it's like very important. This is called the unknot. This blue thing, this blue circle. Like it's a piece of string that hasn't been knotted in any way. It's just open. The next one is called the trefoil knot. The first picture that you see over here on the left is the classic version of the trefoil, and the other six pictures are like they are deformations of the trefoil. It's like you're twisting the trefoil knot around until it like looks a little different. But basically, if you perform some transformations on the trefoil knot, on these deformations of the trefoil knot, you'll ultimately get any one of the other ones. And then lastly is the figure 8 knot and some of its deformations. So yeah, so I added a line like, why care? Well, once upon a time chemists did. So there's this book by Colin Adams called The Knot Book, which kind of gives a brief history of how the study of knot theory came into existence. So apparently in the 1880s, Lord Kelvin, the physicist Lord Kelvin, he was convinced that, so you guys know about ether, right? The hypothetical uh, the hypothetical element which like was considered to surround all which was considered to be present in vacuum, like what we now call as vacuum, and like yeah, in which light would travel, and Michelson Morley kind of destroyed that. Anyway, so Kelvin was kind of convinced that elements, that atoms of elements actually exist in the form of knots. I have no clue why he thought that was possible, but yeah, he did. And like he was kind of obsessed with the idea. Him and another person, I can't recall the name of that person. They were obsessed that if they could find the like number of distinct knots possible, each of those would correspond to a new element. Like say the trefoil would, for example, correspond to the hydrogen atom embedded in ether. Say the figure 8 knot would, for example, correspond to the oxygen atom in ether, and so on. So anyway, after that, Michelson-Morley performed their very famous ether experiment, and they kind of disproved the existence of ether, and chemists lost interest in knot theory. But by then, mathematicians became interested in it, and so they decided this is cool. Let's take this area forward, and so knot theory kind of flourished in the 20th century, and it's now a very cool area. I'll just present like one very cute result from knot theory that I read from Russell's book in the next note. So yeah, any questions? No, right? Okay, yeah, this is very intuitive stuff. So just give me a second. I'll have some water. Nice pun, Arvind. Okay, so knot invariants they're a very cool area of knot theory. So a knot invariant is a feature of a knot that does not change upon deformation and helps identify if two knots are different. So basically, if two knots have the same knot invariant, you can't say that they are like deformations of the same knot. But if two knots have different knot invariants, different values of the knot invariant, you can definitely say that these knots cannot be these knots can't be converted from one to the other. So okay, I kind of gave away the thing, but okay, take a look at the trefoil knot. Do you think it can be unknotted? Like that is, it can be transformed into the unknot. Anand knows the solution to this.
Yeah, so does Varun.
Yeah. Oh, Varun's here. Hi, Varun. So yeah, I gave away the answer because that's right on the top of the slide. So yeah, so the trefoil is distinct from the unknot. I can go on and on for years and years, but it's like totally impossible to unknot the trefoil knot. And we'll do a really cute proof of this. So there are these moves called Ryder moves, and Meister moves are they are of three categories. This is move number one. So basically, Meister moves are a sequence of moves that you perform to deform a knot. And this is a theorem which we will not prove because the proof is pretty long. Two knot diagrams come from the same knot if and only if they can be obtained from each other by a sequence of the following three moves. That is the following categories of Meister moves. This is move one, which is basically if you have just a twist in the knot, you are opening it up. Move two is you have one part of the knot going completely on top of the other part of the knot, and you just pull them apart nicely. So you're not tearing or doing anything, you're just neatly pulling them apart. And move number three is just you have two parts, you have two strands of the knot, one on top of the other, and you have a third strand on top of them, and you're just sliding the third strand. So these are the only possible moves that you can perform. All other moves that are used to deform a knot will be a combination of these moves. So next we come to a couple of definitions. A strand in a knot projection is a piece of the knot that goes from one undercrossing to another with only overcrossings in between. So here's a diagram, and you guys can see my mouse pointer, right?
Yeah.
Okay.
Yeah.
So a strand is like it's each one of those colored parts. So I'm going from one undercrossing. I have an overcrossing in between. It's still a part of the strand. I go from this undercrossing and I reach here. As soon as I reach an undercrossing, I consider the next part of the knot to be the next strand. Then I have this one. It starts from an undercrossing. I move over a part of another strand and I come back and reach an undercrossing, and that's the second strand. I completed moving on the second strand. And the third strand is like it goes from this undercrossing and ends here. That's a strand. Next, I have this definition of tricolorability. A knot projection is said to be tricolorable if each of its strands in the projection can be colored by one of three different colors, such that at each crossing either three different colors come together or all the strands have the same color. Furthermore, at least two colors must be used while coloring the projection. So a knot projection is basically one of those diagrams of the knot. For example, this, or like as we had in the previous one. All of these are knot projections of the trefoil knot. All of these are knot projections of the figure 8 knot. So that's a knot projection. So when I'm tricoloring a knot projection, I think this is the nicest way to explain it. So I have this crossing, and all the knot strands that come here are colored in the same color. So this is a not this does not violate tricolorability. I check for the other two crossings and I see that at the lower one I have three colors coming together at the crossing, and at the upper one also I have three colors coming together at the crossing. So this diagram does not violate tricolorability. And also my unknot cannot be tricolored because I cannot use three different color. I cannot use more than one color to color an unknot, because like there are no undercrossings there are no undercrossings at all. So if I can show that the trefoil knot will always have this property of tricolorability, I can basically conclude that my trefoil and my unknot are two distinct knots. But yeah, before that, I need to prove that Ryder Meister moves, which are used to deform knots, can preserve tricolorability. If I can do that, then tricolorability basically becomes a knot invariant, because the only way I can deform a knot is by these Ryder Meister moves. And if Ryder Meister moves preserve tricolorability, then tricolorability is not violated when going from one knot projection to another knot projection. So does that hold? And the answer is yes, as we shall see here. This is move 1, like, or rather both of these are move 1. So if I'm considering the diagram on the top, when I have this untwisted part of the knot, say it's in the color black, and I'm just twisting it. So after performing that twist, I can just leave the twisted knot in the same. I can leave this twist in the same color as I started. Then both of these are tricolorings, because there's this one undercrossing here, and like both of the strands that I see here, they're actually one strand. But yeah, both of these things, all three of these broken lines that I see here are in the same color. So it's a tricoloring. And the next one is basically I have this twisted part of the knot and I'm opening it up. And I claim that this is always at this is always going to be a tricoloring. The way it works is that the LHS will always be colored in one color. If it's not colored in one color, then it's going to look something like this, which is not a tricoloring. So I have the LHS, and it's going to be colored in one color to preserve tricolorability. And I can just open it up and leave it in the same color as we started. So for move 1, I don't have any problems. Like move 1 of the 3 Meister moves does not affect the tricoloring. Next, I check for move 2, and I think this is the only critical move that we need to check because the others are kind of trivial. In move 2, I start off with the LHS, and I have a tricoloring here. Like, or at each crossing, I can see that the 3 strands are in 3 different colors. So it's a tricoloring. When I open this thing up via move 2, I see that I have 2 strands and they're in 2 different colorings, but they're not crossing over. So if the rest of the knot is in a tricoloring, this move is not going to, these 2 strands, because they're not even crossing over, they're not going to affect the overall tricoloring of the knot. Hence, move 2 also preserves tricolorability. And yeah, if I go from the RHS to the LHS, I can just like reverse the order. So I think I should just like mention one thing. Tricoloring is not, it's something that I choose. So it's like if I want to do a tricoloring of a knot, it's something I will do at each stage. I just need, what I'm doing here is that I'm just trying to show that even if I perform these Meister moves, I can still color my knot in a way that tricolorability is preserved. Not the coloring itself, but the property of tricolorability. So yeah, this is move 2. And move 3 is kind of trivial. It's like you have the LHS and you just shift the third lower strand up and you get the RHS, and vice versa. I should have added like a double arrow. But yeah, in both of the diagrams, you can see that tricolorability is preserved. So I can basically conclude that Meister moves preserve tricolorability. And now, if we look at the classic projection of a trefoil knot, we see that it's possible to tricolor a trefoil knot. But like an unknot, on the other hand, I should have attached a photo here, but anyway, an unknot, as we can see here, it can be colored in only one color because there are no undercrossings at all. So an unknot is not tricolorable, but a trefoil knot is very clearly tricolorable, and because tricolorability is a knot invariant, I can conclude that the unknot and the trefoil knot are 2 distinct knots, with the consequence being that the trefoil knot can never be opened up into an unknot. Hence, a trefoil knot cannot be unknotted. QED. Any questions? Lol, so many puns. Anand, what do you mean by tricoloring? Oh,
I had a quick question.
so many puns. Wow. Okay.
But I had one question, Ipsa.
Yeah, sure.
So can you go back to move 2,
Yes. Just a
the
second. Yeah.
tricoloring, this one, yeah. Is there any reason that both are blue on the edges, or like the other one can be any other color?
Oh, no. That's what I said. Now, you are basically choosing a coloring of the knot so that you can show tricolorability. I just chose it to be blue.
I
The
mean, like,
reason I chose, yeah, are you asking me about the RHS?
no, the LHS.
The LHS. The reason it's blue is because there is some other area of the knot where the strand started out blue. No, wait, I
Okay.
don't think I totally got your question.
Like the top part and the bottom part are both blue. So is that just arbitrary? Like, does it have no
Oh yeah,
meaning?
so yeah, it's kind of arbitrary. I just wanted to show that there are like three different colors at each crossing, which
Okay.
is working out here. And I wanted to do it with the least possible number of colors because I'm lazy.
Right. Fair enough. Yeah. Yeah. The
Yeah,
efficiency
wait,
makes sense. Okay.
I don't. Oh wait, sorry. Yeah, it has to be colored by one of three different colors. Sorry. Yeah, it has to be one of three different colors, which is why like the top and bottom ones are blue. I can't use more than that. Yes, sorry, my bad.
Okay. Okay. Fine. All right. Cool. Thanks. Yeah.
You're welcome. Okay, so this ends part one of the talk. Like the small part on knots and basic deformations and all. Next, we'll move to something called a vector field, which is something, yeah, it's pretty cool. We'll prove the fundamental theorem of algebra using this concept. So a vector field, a continuous vector field is said to be specified on a plane if at each point of the plane, a vector can be specified in a way that the components of the vector field depend continuously on the point. So you have a plane, and at each point of the plane, you want to specify a vector, and the components of the vector field, like they are continuous functions of the point. You do not want like quick jumps happening in the vector field. So yeah, that's the way we defined it. And a point at which this vector field is zero is called a singular point. And the next definition is very important. The difference between the number of positive and negative revolutions of the vector field around a singular point is called its index. So let's look at the three pictures below. So the center of this circle kind of thing is a singular point, which is why there is no vector here. And if I look at the vectors around it, I can see that when I'm moving clockwise, so I'm taking the anti-clockwise, anti-clockwise. When I'm taking the anti-clockwise direction to be positive and the clockwise direction to be negative. Like I should have written that down, but I forgot. Anyway, that's convention. So when I'm moving anti-clockwise, I see that the vectors are also moving anti-clockwise. Like the angle made by the vector with the like imaginary x-axis, which I assume to be somewhere over here, is increasing. And the vector field completes one revolution around the singular point. There are no negative revolutions. So I can say that the index of this singular point is 1 because it's positive and there is one full revolution when going around the singular point. Next, this is another singular point. And here is the, okay, I'm just starting here because this is like where I'm fixing my imaginary x-axis. So this vector is pointing downwards, and as I'm moving anti-clockwise, my vector is moving, my vector field, the vectors on my vector field are also moving like anti-clockwise slowly. And when I move around this singular point, I can see that my vectors are also moving anti-clockwise, and they ultimately, when I reach the first point, the initial point where I started off from, I see that my vector field has also completed a positive revolution, and there are no negative revolutions. Hence, I say that the index of this singular point is 1. The third one, so my singular point is over here because like the two vector fields are cancelling out. And I can say as I'm moving like this, So this is my imaginary x-axis and I'm moving this way. As I'm moving like this, I can see that on both sides of my vector field, my vectors are kind of like moving in this fashion. Like I'm moving like this. Vectors are, I'm moving like this, and my vector field is kind of like moving in the other direction. That's kind of like in the opposite clockwise direction. So I say that the index of this singular point is -1. Any questions? Okay, I'll just proceed. So next we have a lemma, and this lemma is kind of like the stepping stone we need to complete in order to prove the fundamental theorem of algebra using vector fields. The lemma says if two vector fields v and w are given on a non-self-intersecting curve in such a way that at any point x, the vectors v of x and w of x do not point in exactly opposite directions, then the indices of the curve with respect to these vector fields are equal. So it's like I have, so here's the picture. I have v and I have w, and like they are not going to be exactly opposite each other and like basically cancelling out anywhere on this circle. And my claim is that the indices of like my curve here is a circle. The indices of the circle with respect to both v and w are equal. Basically, like they perform the same number of positive minus negative revolutions over here while moving like over the circle. So to prove this, what I'm going to do is I take a point x, and this is the vector field the v. This is the vector field w. I consider like, so these vector fields, they have a magnitude and a direction. So at the point where these two stop, I draw a line between them, and I consider some variable t which lies between 0 and 1, and I consider no, sorry, it doesn't have to be, it's just, sorry, t is not between 0 and 1, t is just any integer, any non-zero integer. So so I section this line segment joining the terminal point of v and w into a 1:t ratio. And the point of this sectioning, I draw a vector from x to this point, and I call it v of t. So like v of t lies between v and w. And because it's lying between them and they are not pointing in exactly opposite directions, v of t can never be 0. And like basically, because it cannot be 0, I'll have like, it's never going to be 0, hence how do I, it's basically never going to be 0, hence I'm not going to encounter any singularity along this point, and hence like the indices will be the same for both v and w. Any questions?
I didn't get that last argument. Could you just elaborate on that a bit? I'm not too clear.
Okay. Just give me a second. How do I explain this? So basically what you want to show, like if you want the index to be the same for both v and w, you don't want any You don't want any, like you will want the same number of rotations being performed by both of these vector fields. So basically there shouldn't be any singularity in between them, right? So like if any vector between them, if any vector lying between V and W is not zero, then this they're going to perform the same number of rotations as I move along this circle, right?
Yeah, I think I get it now.
Yeah. So yeah, right. That's the argument, because they're going to perform like, and after that is like basically the definition of an index. If they're going to perform the same number of revolutions, they're going to they're going to have the same index. So as long as there is no singularity in between them, I'm like, I don't have any issues, right? Any questions?
I'm assuming this can be generalized to like vector fields on arbitrary manifolds, right? And okay, so my question is what does this index thing look like symbolically? Like, how do you compute an index? I mean, I get the intuition, but
So I'm not sure if this is a very conventional technique, okay? I'm not entirely sure if it's used in like, if the concept of an index is regularly used in like algebraic topology. I think Poincara's Soul conjecture sort of uses the idea of an index, either the Soul conjecture or some other conjecture of his. Like it's based on the idea of an index, but how it looks, as in the next section is actually about the vector fields on a sphere, so you'll get an idea when we go to the next section. Okay, I'll just give you a
okay,
teaser.
cool.
I'll give you a teaser. It looks like this. These are vector fields on a sphere, and this is basically an index because there is no vector flow over on this point, and likewise there will be one on the other pole of the sphere, and here is another vector field which has only one index, which has only one singular point.
Singularity, right? Okay.
Singularity, yeah, one singular point, but it's going to have an index too, because like to preserve continuity, the only way I could draw a vector field is in this way. And we'll do a theorem. We'll do a theorem which is kind of based on this idea, but let's get to the fundamental theorem of algebra before that.
Cool.
Yeah. So the fundamental theorem of algebra says if I have a polynomial with complex coefficients, I'll have at least one complex root. Simple to state. And I was pretty surprised that the idea of like this kind of geometric idea of an index led to such a cute solution of this led to such a cute proof of the fundamental theorem of algebra. So I take two vector fields, v of x, which is z bar n, z and n being the same as the degree of the polynomial, and w of x, w of z, where the value of the vector field at the point z is given by p of z. Now I take a large r, a large value of radius, as large as I want. I'll calculate a precise value later. And for any point z on the circle mod z is equal to r, we have basically I take the difference between the two vector fields at that point, and it's never, so if I take a to be the maximum value of the coefficients, then this the absolute value of the difference between the two vector fields for any value of z will never exceed n into a into r power n minus 1. So if I take my circle to be greater than NA, I have r power n is greater than n a r power n minus 1. And r power n is basically the value of v of z, because I'm taking mod z to be equal to r. So I can say that the absolute value of the difference between the two vector fields at any point z will never exceed the value of v of z. For a value of like for a circle with radius greater than n into a. Now, if I examine this inequality closer, I can see that if w of z and v of z are in opposite, like diametrically opposite directions, this is never going to happen. Because if they are in diametrically opposite directions, these two values, like magnitude wise, will add up. And if they add up, they're not going to be smaller than the value of v at z, right? So basically I conclude that v of z and w of z will not point in diametrically opposite directions on the circle mod z is equal to r. Hence, by the previous lemma, the index with respect to w is equal to the index with respect to v. Now, v of z is like a very neat sort of vector field. And it's easier to the entire reason why I did all of this is because it's easier to find the index using v of z, the index of the circle using v of z. So since I'm considering a circle, I can take z to be equal to this should be capital R. Why did I write this as small r? Let z equal to r e power I theta. Then v of z becomes r power n e power I theta n. And if you think about it, the index of the circle with respect to all singular points inside it is going to be n. Because if I take a point on the circle, I take a point here, and I move along the circle by 2 pi radians, v of z is going to change by n times 2 power n times twice pi, is going to rotate n times. So the index with respect to v is n, and so is the index with respect to w. So if I consider the index, so I forgot to write down one theorem. It's pretty easy to visualize. Basically, if I consider the index along a general curve, it's going to be equal to the sum of the indices of all the singular points inside the curve. And the way the argument provided that the number of singular points is finite. And the way the argument for this holds is that if I have a general curve and I have like I'll just draw it in paint. Just give me a second. I'll just share my screen again. Share paint. So these dots are the singular points. They are finite. And I have this curve. It looks very bad. But basically, the index of this curve, I can shrink my curve and kind of make it very, very close to these singular points. Because there are no other singular points in the space. I'm just basically deforming my curve, and I'm bringing my entire vector field as close to, as like surrounding the singular points as possible. So whatever index I have is kind of like generated by these singular points. Right. So going back to Evernote, I apply that idea. So here, so the index of the circle is n, and whatever index is coming from this circle is going to be caused by these singular points inside the circle. So if the circle doesn't have any singular points, I can kind of like contract the entire circle down to one point. Basically, like, can you see this? Can you sort of visualize it? Like, I can just shrink it down to one point. And I can accordingly shrink the vector field also because it's continuous. And hence I can conclude that there will be no index for a circle without any singular points. So in my in this proof that I'm doing, I have the index of this vector field V being equal to n, and n is non-zero because like this polynomial will have a non-zero degree. It's not a constant polynomial by assumption. So there has to be some singular point inside the circle. And this singular point will correspond to both W and V because they have the same indices. Hence, and W is the value of W at any point Z is equal to P of Z. So basically my entire argument translates to like saying that there is a point inside the circle mod Z is equal to R where P of Z vanishes. Hence, there is a point inside this circle mod Z is equal to R, which is the root of P of Z. Hence proved. Any questions? Hello, am I audible?
Yeah, I mean, we can hear you.
Yeah. Any questions? Shall I? Okay, cool. I'll just take that as a no. So yeah, I really like this proof because it's very cute. And like, where this was where I realized how this concept of an index is so important. Anyway, moving on. Next, we come to vector fields on 2D surfaces. And like, as I'd shown you just a little while ago, here are two pictures of vector fields on a sphere. And you can basically notice that picture 1 has two singular points. Hence, the overall index of the sphere is going, and like at each of these singular points, the index is 1. Like this is one rotation, and this is likewise for the other one. It's not visible here because it's a 3D figure and this is a 2D plane. Anyway, so the sum of the indices for the two singular points is going to be 2. And on the figure on the right, I have a continuous vector field with just one singular point. And the way they've drawn the way they've been able to draw this vector field is such that there is the index of the singular point is 2. Like this is one rotation and this is another rotation. So overall 2. Which leads us to the question, can we draw a vector field on a sphere such that the with a finite number of singular points, such that the index of these the sum of the indices of these singular points is not equal to 2? And turns out no, we'll always have the sum of indices being equal to 2. So why does this happen? First, let's consider a definition. We define a great circle as a section of the sphere by a plane that contains the sphere's center. And how long can this go on, this talk?
I mean, I think any time is fine. Like we started around, we started around at 3:15. So I guess
he means 5:50.
Yeah,
No,
fine.
it's informal.
5:50.
It's an informal thing anyway, so I think like you can go on as long
I
as
don't have
you
much after this. Like I'll use this concept of a vector field on a sphere to prove the Euler formula that V minus E plus F is equal to 2 for any convex polyhedron. And after that, I'll just state the classification theorem of like compact surfaces. So yeah, I guess, yeah, fine.
Yeah,
The reason I was asking was, what?
There's no time limit. I mean, like Kanna took 2 hours for this talk, and like I took slightly over an hour, so it's okay.
Sure, fine. Then I'll do this proof also. So there, I claim that I can have a great circle on a sphere such that it avoids all the singular points, provided the number of such singular points is finite. And how do I do this? I mean, intuitively, it's kind of clear, right? The number of singular points is finite. I just choose a great circle that avoids them. But so I'll prove this now. So I'm considering a correspondence A comma A star goes to small a, where capital A, okay, I missed out the capital, fine, yeah, sorry, this is a general definition, yeah. So capital A and A star are any two diametrically opposite points on the sphere, and small a is a section of the sphere which is perpendicular to the line joining capital A and capital A star, and contains the center of the sphere. Because if it was just any section of the sphere perpendicular to the line joining A and A star, I could take a section over here, but that doesn't contain the center of the circle, the center of the sphere. So this is A. And as you can see, the boundary of A is a great circle, right? So if I can, let my singular points be A1, A2 up to AN, finite. And the corresponding sections on the sphere are A1, small a1, small a2 up to small an. Kind of like this. I'm just drawing the sections over here because drawing the points also would be a little bit messy. So anyway, because I have a finite number of sections, I can always find a point on the sphere which does not lie on any of these sections. Now, this is M, a point which does not lie on any of these sections, small a1, small a2 up to small an. And I call its diametrically opposite point as M prime. M prime or M star, like whatever. I was tired of typing out stars and like making them superscripts, so I just used M prime. So I can draw a line joining M to M prime and consider a section perpendicular to it. Kind of like this. this is M, this is M prime, and I consider a section small m perpendicular to it and containing the center of the sphere. And I claim this section M will not contain any singular points. Like suppose it contained a singular point, say n. Say say this was a singular point. Then the line, then the corresponding section perpendicular to n and its diametrically opposite point n star would contain capital M, which would be a contradiction because I'm constructing, because I'm choosing M in a way that it avoids any of these sections, right? Hence, this section small m does not contain any singular points on it. And the boundary of M will not contain any singular points, and it's a great circle. Hence, I'm always able to choose a great circle which avoids any of the finite number of singular points on a sphere. Now, that's like part one of the, that's a small claim I'm making as a part of the proof. Now, why is my screen not moving? Sorry, Chrome is hanging up a bit. Just give me a second, it's not responding. Okay. I agree with you, Anand. Chrome is a pain sometimes.
Always.
Wait, why is this not moving? Okay, it's moving now. Now, the next step in the proof is I'm assuming, so if I imagine my sphere to be like a football, I'm just like pumping out all the air inside it and deflating it. Then I can kind of flatten it to form a double disk. Like you can see that, right? When I flatten it out to form a double disk, and yeah, I do that flattening using the great circle small m as my reference point, as my reference circle about which I am doing the flattening. So if I have a vector field going like this, after the flattening operation, this vector field kind of forms two different vector fields, one like this and one going this way. It can't be the same vector field because there is like a sharp jump. It's not continuous. So there are two different vector fields, like one on the upper half of the upper hemisphere of the sphere and the other one belonging to the lower hemisphere of the sphere. And they are, as is evident from this picture, they are symmetric about the circle M. I can take a perpendicular and they'll form the same angle again, like with respect to this perpendicular. Now, in the next part, I claim that if I have two vector fields symmetric about the boundary circle, the sum of their indices will be equal to 2. And the way I'm doing this is I have a circle. Like these are some geometry arguments. This is like the point about which I'm currently considering the vector fields, and this is V and this is W. and this is the angle formed by V with respect to an imaginary x-axis. It's phi. Let me call this phi1, and this is the angle formed by W. It's phi2. Now I consider a zoomed up version of this over here. So this is my reference point X, and this is phi1, phi2. So XB is V and XD is W, and XC is this tangent. This tangent I am drawing about the point X, tangent to the circle about X. So now I consider phi1 plus phi2, and with a little bit of algebra, I get this. So it's basically like phi1, phi2 is phi1 plus this angle bxd, and like bxd is twice of bxc because the two vector fields are symmetric about this tangent line, and like phi1 plus bxc, which is this part, is equal to 90 degrees plus alpha. Alpha is the reference angle formed by x with respect to the x-axis with respect to the center of the circle, and this angle is 90 plus alpha. So this angle is also 90 plus alpha, and this angle is twice of this angle is equal to phi1 plus phi2. Hence phi1 plus phi2 is 180 degrees plus twice alpha, and phi2, I just take phi1 over here, and I have phi2 is equal to 180 degrees plus twice alpha minus phi1. Now phi1 per phi1, suppose V goes through n revolutions as x covers the whole circle. So when I'm considering the index, I have to move over this entire circle and assume V performs n revolutions. Then delta phi1 is going to be twice pi n. Alpha, which is the reference angle formed by the point x, like with reference to the center of the circle, that's going to change by twice pi because I'm moving across the circle. So delta of phi2 is going to be equal to twice delta of alpha minus delta of phi1. So it's twice delta of alpha minus delta of phi1. That is 2 into twice pi minus twice pi into n, which is twice pi into 2 minus n. Now this twice pi component of the change of the angle will correspond to 1 revolution each. And hence 2 minus n is giving me the index of the vector field corresponding to phi2, which is w. W corresponds to phi2, V corresponds to phi1. Index of V is n by assumption, and the corresponding index of W is 2 minus n. So the sum of the indices of V and W is equal to 2. Now where do V and W come from? They basically come from when I again stretch out this entire sphere. They're coming from the original vector field on the sphere. And deformations do not affect the index of a circle because it does not change the number of singular points. So I can say that the original index with respect to the original vector field is going to be 2, which is what I wanted to prove, hence proved. Any questions? Okay, I'll take that as a no. So you might ask, why are we doing all of this? And that's because we're building up the background for proving the Euler-Descartes theorem. The Euler-Descartes theorem is like we've all done it in school. It says if V is the number of vertices, E is the number of edges, and F is the number of faces of a complex polyhedron, then V minus E plus F is equal to 2. And the way we prove it is, so suppose I have a polyhedron and now I consider a sphere kind of encompassing the entire polyhedron. And the way I choose the sphere is that I have to make sure the center of the sphere lies inside the polyhedron. Then I project the sides of the polyhedron onto the sphere using the center of the sphere as a reference point. So like if this triangle was on the original polyhedron, then I use this as this is the center of the sphere, and I'm kind of like projecting this side over here on the sphere. So I guess you can like kind of assume that this is a curved space and like this is getting projected onto the surface of the sphere. Then this line gets projected onto the surface of the sphere. And this line will also get projected, but because it'll look kind of bad, I didn't draw it over here. But it's kind of like it's getting projected over here too. So that way I'm projecting the entire the sides of the polyhedron onto the sphere, and I'm getting kind of a curvilinear network corresponding to the sides of the original polyhedron. Now, I choose a point on each face of the polyhedron network on the sphere. So the diagram I have here, it's taken from Prasalov's book. He doesn't kind of like represent it on a sphere because like same arguments, it just doesn't look very nice on a sphere. So he's just showing it with reference to the original polyhedron itself. But like when I'm choosing these points, I'm choosing them on the sphere. It's just like this is for diagram purposes only. So I'm choosing a point on each face of the polyhedron, not necessarily the midpoint, like even though it looks like it's the midpoint, it's not necessarily the midpoint of the face. And suppose two of these points are on adjacent faces, then I'm joining these 2 points by a vector which passes through this midpoint of this common edge. Because like on a sphere I can have like multiple way, almost an infinite number of ways of going from one point to the other, but like if I choose a third point, then there's only one like curved line that can go through them, all three of them. So that's fixing my vector. And the way I'm assigning the vector field is that I'm assuming the vector to flow from this point to the center of the edge and from this point to the center of the edge. And I'm also assuming that like the way the vectors are flowing is that from each point that I'm choosing on the face, the vectors are just moving out. Okay, where they're going, we'll get to that. They're moving out. And for each vertex of the polyhedron, the vectors are all coming into the vertex. And by the previous construction, if I have like a line, a curve going from the center of one face to the center of the other face, then the vector will be directed towards the center of this midpoint of the edge. So I've added a diagram here. This is how the vector field looks like at the various points on the curvilinear network. For a face point, they're all moving away. For a vertex point, they're all coming towards it. And for an edge point, it's kind of going to be a mix. So this line these vectors that are approaching the edge point are coming from the two different face points. The vectors that are going away from the edge point are ones that are going towards the vertices. And these are like basically some others that are just like moving around avoiding this point. It's a mix of all possible arrangements or vectors. Anyway, now it's clear that all these points are singular points. And the way I'm defining this vector field, it's clearly it's continuous, first of all, hence it's a vector field. Hence, there are no other singular points. Clearly, like that. That's how I'm defining this vector field. And if I look at each of these points, this clearly has an index of 1. This also has an index of 1 because I'm moving like clockwise, because the vectors are moving clockwise as I'm moving clockwise. And this, as I'm moving clockwise, I see that my vector is actually, as I'm moving anti-clockwise, I see that my vector is moving clockwise till here. And when I'm going this way, the vector is also moving clockwise over here. Hence, the index of this point is going to be -1. So there are f number of face points, and the index corresponding to the face points is going to be +f. There are v vertices, hence the index corresponding to the vertex points is going to be +v. And there are e edge points, so the index corresponding to the edge points is going to be -e. So the sum of the indices on this curvilinear network of like curvilinear vector field on the sphere is v minus e plus f. But from the theorem in the previous note that we did, we know that the sum of indices is going to be equal to 2 for any vector field on a sphere. Hence, I can conclude that v minus e plus f is equal to 2. So QED. And with that, we end like the second section of the second part of the talk. And basically the main talk itself, because next I'll just be talking about the classification theorem for surfaces. But before that, do you have any questions on this theorem, on the proof of this theorem? Anyone? Yeah, I never liked the induction proof. Okay, so since there are no questions, I'll move on to the classification of surfaces. I am not doing the proof because first of all, there is a significant amount of background I'll need for this. Secondly, because I don't understand the proof myself. It's that advanced. Like yesterday, I was looking for simple proofs of the classification theorems, and I found this book called A Guideway to the Classification Theorem of Surfaces. Like there are literal books written on the proof of this theorem. But it's very cool. So first of all, I have like a 1D space, and like for us fourth years, I just call it a 1D, a one manifold. I won't define a manifold because it'll just take a very long time to do that. Like I'll have to define basis and all that. But yeah. So for Varun, Varun, do you know basic topology? Like just manifolds and all. The definition of a manifold, just that. Hello, Varun. I guess he's typing. Anyway. Oh, cool. If he knows Lee stuff, he probably knows the definition of a manifold. That's fine. So a manifold is like a topological space which is locally Euclidean. If I consider a very small piece of the manifold, it will look like a section of Rn. I just zoom into a very small piece of it and it looks sufficiently flat. So any one-dimensional manifold will be homeomorphic to one of the following: a circle, close interval 0, 1, close 0 to open 1, or open interval 0, 1. The proof of this involves something called Morse theory, which I don't know much about. I think Karthik has been reading some stuff about it. He'll have a better idea of it. But yeah, it's a pretty advanced proof, and these two people have given proofs of this classification of 1D spaces, Milnor and Hirsch. The next one is called the classification of compact connected surfaces. A surface is basically a two-manifold is called a surface, a two-dimensional manifold. It's a surface, and any compact connected two-dimensional manifold or surface is, so if M is orientable, it will be homeomorphic to the sphere or to a connected sum of tori. So it's either going to be homeomorphic to the sphere or to the torus, or this is a double torus. So by connected sum of a torus, what I mean is I remove a small section from one torus, I remove a small section from another torus, and I just join those two. Because I'm removing small sections, the overall structure that I get will remain two-dimensional. So these are all hollow objects, okay? That's important. There is nothing inside them. These are just surfaces. So any orientable surface will either be homeomorphic to the sphere or to a torus or to a double torus or a triple torus and so on. And the number of tori that I have used in making this connected sum is an invariant called the genus. And if M is non-orientable, then it is homeomorphic to the connected sum of projective planes. So this is an artist's representation of the projective plane. Basically, the projective plane is like it's like I have a sphere, and I just go to this dummy picture of a sphere that I have. I have a sphere, and any two diametrically opposite ends of the sphere are identified. Or the other definition is I have the space of lines passing through the origin, and that is also called the projective plane. The space of all lines passing through the origin. So it basically looks like this because there is an identification of diametrically opposite points on the sphere going on. And yeah, it looks cool and scary at the same time. And here is my very famous Klein bottle. And I don't know if you guys know this, but the Klein bottle is actually obtained from the connected sum of two projective planes. There are cool YouTube videos of that, which you can check out. The number of summons is in this connected sum is an invariant, which is called the non-orientable genus of the surface. And yeah, so any compact connected surface that I have will be homeomorphic to this small to any one of this small collection of surfaces that I have mentioned over here. So the ramification of this classification theorem is that if I can study all possible properties of the sphere, the torus, connected sum of tori, and the projective plane, I can completely understand any compact connected surface. And basically, if I have like a surface that is not connected but it's compact, it's going to be like each of the disjoint components is going to be a compact connected surface in itself, and hence I can understand the properties of any of those disjoint, like all of those disjoint components of the surface. So basically I can understand any property of a compact surface. So like uh, any yeah, I can, and this classification has been done, hence you can kind of conclude that we pretty much understand everything that there is to understand about two-dimensional manifolds. Now so there is a like simultaneous project going on, which is the classification of 3 manifolds and 4 manifolds, because those are the only manifolds for which like the classification has not been completed. So the hope is that we can someday classify 3 manifolds and 4 manifolds, and after that pretty much understand all that there is to understand about manifolds in general, because once they are classified I can study the properties of any of those like any of those small group of objects that they are homeomorphic to, and hence basically I have understood everything there is to understand about them. And here are some references. So this is the main reference, Intuitive Topology by V.V. And this is the one from which like the bulk of the talk, except the concept of tri-colorability, comes from. Tri-colorability has been done in Prosolov's book, but in a slightly different manner. The one that I used in this talk is adapted from the Knot book by Colin Adams, which is another really good book. It's on knot theory, not topology. And like I haven't finished reading it completely. Once I do, maybe I'll give a talk on it sometime later. And the third one, Introduction to Three Manifolds by Jennifer Schultens, is a graduate level textbook from which like I have taken this part on the classification of surfaces. This part is not from Prasolov. This is like standard stuff that I read over this summer. And Schultens includes a proof of the classification theorem of compact surfaces, but like it's very long. It will take over an hour to complete that. So maybe sometime later. There is a smaller proof of the classification theorem of surfaces, but that involves a lot of homology and I don't understand it, to be honest. So yeah, with that, I end my talk. So thank you.